So did I tell you guys that recently in Zoom? Hello, Niranjan.
Morning.
Got late. So recently in Zoom, did I tell you guys this, that there is this option in the last 2 weeks, I think, 2 or 3 weeks, there is an option on Zoom saying that they will give you a summary of what we did in the class. And it's AI generated, so called, like we have ChatGPT has really changed the scenario. So there is this summary it gives, and every day after the lecture, I get a summary, which I would say is decent. I mean, it's not correct at all, but at least it captures some of the, out of maybe 10 sentences, it gets in the summary. I'm saying not the sentences I say, it is its own sentences. It gets about 4 right. So it's kind of interesting.
Yeah.
So if you guys want, I can pass
Yeah.
it on to you, but request it instead of me telling it, because I have this, I'm the teacher, right? So whatever I do, it becomes important in a sense. So I don't think it is relevant enough that I should share it with you guys. But if you guys are interested, or I want to see what this summary is.
So is it like printed document?
Yeah, it comes as an email to me.
Okay.
After every lecture, after every recording, it gives me a summary. Now, I should add something to this. This one does not come out that great. As I said, maybe 30% is correct of the essence. But then I also have a meeting with a 10th grade student. He's my nephew. Every day I meet with him and we talk about random stuff. I'm supposed to teach, but I don't teach him. We just chat. And I do that every day. And that summary is quite good. I don't want to say quite good is like 2 adjectives, right? No, like I would say it gets maybe 60 to 70% correct. Because there we are talking normal stuff, like the stuff we talk about is very available on the internet. But this is a little advanced topic. It has difficulty. There is not much data there, even though there is a lot of complex analysis out there, but still compared to the whole internet data, this is not so much.
But about the privacy.
Oh, privacy is gone. I mean, the moment you're on the internet, there is no privacy. Oh, that's absolutely no privacy, I would say. Probably like the moment, I mean, we are on video, probably that is, if you go by my picture, I think internet is probably full of mine. So yeah, I think, yeah, that's it. Yeah, privacy is a different question altogether. I believe that the moment you go on the internet, there's no point in worrying about privacy. Instead, what I typically say is that cheat the system, right? It's not very hard to cheat the system. Like, for example, usually you say that, oh, whatever you're searching, it's trying to characterize you with those searches. Give them some wrong searches, right? Every day, spend 1 minute on giving wrong searches. I mean, programs are pretty stupid. Right? So just give them, so mislead them, and then they don't know your character, right? So
A transcript or just
it's a transcript. It's a transcript.
the entire class or just
Entire class. It's about maybe, I would say, if you were to print this out like this, maybe 2 pages with titles. Like it breaks it into maybe about 20 subtitles, right? Saying that first Cauchy's theorem. I mean, it says, and sometimes it gets it wrong. Even the essence it gets it wrong. But roughly, if you read it, oh yeah, that's correct. But I wouldn't recommend using that for any purpose, even for a summary. It's not a reliable data. It makes mistakes. It's not reliable at all. But it's just surprising that, oh wow, it got so much right. Right. And when you imagine that it's a program doing it, it's kind of interesting. So, yeah. Do you guys know how ChatGPT works? No, do you guys know how it works?
No. Just the basic thing.
Huh? Yeah.
Just the basic. They'll write down something. Give the answer.
Yeah, but there is a simple, like I wanted to know what it does at a very simplistic level. I don't do any programming, so but when it got so successful, you ask, I mean, how is it doing it? And if you saw, notice it was really sudden. No one saw it coming, right? It was last November that suddenly there is ChatGPT, and before that there was nothing. I mean, we knew that Google is really good at interpreting, but this was really a surprise. And according to what I read, it was I mean, even the people who wrote it, they didn't expect it to be so successful. But anyway, so apparently it is this. Suppose you have a database, let's say dictionary, right? Let us you have a dictionary of words, like so you want to build a word. So you write A, let's say first you write A, and then the program tries to guess what you're doing, right? So it looks into the dictionary, and there are how many words after starting with A and the next letter, and there might be about 10. Okay, so then next you write a V, right? And it tries to guess the next one. But right here, out of so many, it has this data that everyone who wrote an A, next one they wrote a V, there's a good chance. So they have that data. So that's ranking system, right? Google Rank, all of you guys are aware of. So it goes by rank. That is for websites. Think of words. Like I'm saying complex. There's a good chance that in this lecture I'll say complex analysis, right? That's based on what everyone else has said. So you rank the whole thing. And how Google and other search engines work is that you take the top one and put it. So if V is the top, you give V as the answer. That's how search engines all the while work. But ChatGPT and all this AI came up with this idea that 90% of the time, give it the top search. But let's say 10% of the time, give it random answer. Only few times, give it a random answer, and now you change the system, right? That's creativity. And that's ChatGPT, and it got successful. So instead of giving top searches, just give a small parameter change. It's like saying, when I say that cheat the system, instead of searching the standard things, search something that is not you. And then the system is confused in a sense. So the moment you go out of the top searches, then you're going somewhere deeper inside, and that's sort of creativity. And that simple algorithm is what is being used. And this is mostly said in the language of neural networks and all, but I'm just simplifying it. And this is, I shouldn't say it's my interpretation. This is what Wolfram, Stephen Wolfram, are you aware of? Mathematica, author of Mathematica, the software Mathematica. Are you familiar with Mathematica? Mathematica? No, I'll give you a homework, which is, I use a lot of Mathematica, and I think in the physics, it's useful. MATLAB or Mathematica usually is good. Mathematica, I think, is different from MATLAB. So anyway, so that the creator or inventor or author of Mathematica, and he's pretty good, well known. He's in Urbana-Champaign. So he wrote the book on ChatGPT. I think 50 pages. I read only one page and I thought, oh, I know I understand ChatGPT. So I read one page. So don't trust me, but it's kind of a good understanding, simple understanding of what it is. Anyway, we have to do something important today. Branch cut, and I'm already 20 minutes in. Okay, let's see. And Nathan is not here, I guess. Yeah, homework 7 is over, right? So homework 8.
So it was next Monday or this Friday?
I think last Monday.
So,
You already submitted.
but
This is the next one. This was uploaded last Friday, but I think it was due only on Monday. Like I uploaded it early this time. Is that a confusion? Am I making a mistake?
because there are so many words.
You should ask your teachers not to give homework. I always say if I were to take my own course, I will fail. I don't like doing homework. But that's society, right? You do things that you don't like or you don't believe in. And I really don't believe in homework. I don't think students learn out of forced homework. Like I really honestly believe it because I don't learn. So, but then that's what I do. So, pretty bad example of what society is. A pretty good example of what the what's that hypocrisy of society. Yeah. But I do grade based, so don't take liberties there. So I think I do go by the rule that I make the rule and then I stick to that. So I try not to change the rules in between. So if I made a rule that homework is important, it's important. So, but I don't believe it. Yeah, okay. Let's so we did an example on integration, uh, contour integration. I think it was I think it's a very good example. You have some homework examples also that will help you work on it. Yeah, I think I'll let you guys figure it out. So that there are a lot of details in there. Feel free to ask me, or even if you want, I can do one of the evenings. I can give you tricks to do that. So all this involves tricks. So there's limited time. I can give only limited number of tricks. So sometimes it helps. So if you feel like approach me, otherwise just learn it on your own. Here, this is another example I do, and the third thing, or fourth thing, that's let me write down. So that is this contour integrals. These are the keywords, if you want. Second is branch cuts. Already, this is not covered in standard elementary textbooks. Everyone stops at that stage. And the last one I feel is never done at all is analytic continuation. And each of this you want to do each of this you can do a week or two on it to really get a full understanding of it. Analytic continuation can be a whole course on it. And I will try to do this in the remaining hour today, but give you the essence of it. Like it's like the chat GPT that I talked about. Obviously, you cannot do a program on that, but you get the idea that instead of giving the top, give the next one, and it captures the essence. So similarly, I'll give the main trick, main concept in that, and from there, it's up to you. So let's begin with contour integral. We already did a good bit on that. Let's do an example to clarify that. And that is, I decided to do, let's say, I is equal to 1 over 2 pi. This is a standard integral you might come across while doing various problems. The theta 0 to 2 pi and 1 over 2 plus sine theta. Like you might be doing a problem and in trying to understand model a magnet and interaction between two magnets, and you might get this integral that classifies it. This might be a parameter, but whatever it might be an integral of this kind. How do you do this? First of all, notice this is a real variable. Angle theta is going from 0 to 2 pi. Everything is in real, but you sometimes think that is it possible to go to the complex plane and somehow capture this information. And the trick is that whenever you see the cosine function, this trick always works. So let us do the following. So remember, z is equal to r times e raised to I theta. Right? That's a polar representation of a complex number. It's called Argand. It was popularized by Argand. And if I set r equal to 1, so set r equal to 1, then I have z is equal to e raised to I theta. If I were to look into the complex plane, where does Z sit? In this complex plane, where is Z? On a circle, anywhere on a circle, right? Because I have not given you an angle theta, it can be anywhere on a circle. R is equal to 1, so it's anywhere on the circle. And that's my theta. So this is my Z. So suddenly, when I go from 0 to 2 pi, if I were to think of this 0 to 2 pi as a path on the complex plane, I'm actually going on a circle. Right? So suddenly I'm going from a real world to a complex world. So let's do that substitution. So what is cosine theta? You have this representation that this is e raised to I theta plus e raised to minus I theta divided by 2. And write e raised to I theta as Z. E raised to minus I theta will be 1 over Z, and then there is 1 by 2. That's your cosine theta. I want to change this integral in terms of Z, so I have to replace d theta. So let's do dz is equal to I times e raised to I theta times d theta. That's I z d theta. So my integral is equal to 1 over 2 pi, 0 to 2 pi. And now I'm in the complex plane, so I, instead of saying 0 to 2 pi, I go on a circle in the complex plane. I go counterclockwise, so this is circle. Somewhere I have to say in words that what that contour C means. And d theta is dz by iz, dz over iz. That's 1 over 2 plus 1 by 2, and z plus 1 over z. That's equal to, pull out the I, so that's 2 pi I. I'm on the integrating on the contour, which is a circle around the center of the complex plane. Multiply this z out maybe. So this is dz. And how can I do this? So z, there's a factor of 2. That's simplifies. So it is z times q plus 1 by 2 z plus 1 by 2 z. Multiply it out, so it's 2z plus 1 by 2z squared plus 1 by 2. And simplify again, so pull out a 2 maybe, right? Or what should we do? Yeah, pull out the 2. No, pull out the 1 by 2. So it is z squared 1 by 2, so it is plus 4z plus 1. Quadratic equation like z squared 1 by 2, so that's a 2 is 1, right? So that's the same as, what are the roots of this? So if I were to find the roots, that is equal to z is equal to minus 4 plus or minus 16 minus 4, I suppose. Correct me if I'm wrong. Okay. And divided by 2. That's equal to, that's minus 2 plus or minus, so it's 12, 4 into 3. The 4 cancels the 2, so that's 2 plus or minus 3. Am I right? Think so. Let's call this V1 as -2 plus √3. And the other one has V2 as equal to -2 minus √3. Okay. Is that readable then? Oh, maybe. Yeah. It's really small. So that's so there's a factor of 2 here, put it up. Remember, so if I write it in this manner, 1/2 v square plus 4z plus 1 is equal to 1/2 times z minus z1 times z minus z2. Any polynomial, once you know its roots, can be written in terms of its roots, just the product of them. So my integral I is equal to 1/2 pi I times go over the contour, that is dz. I've taken care of the z as a factor of 2. I put that in the front here, 2. And that is 1/z minus z1 times z minus z2. Whenever this function that you're integrating on goes to infinity, whenever the denominator goes to 0, that's a simple pole. It contributes to a residue that it is not analytic at that point. So 1/z minus z1 times z minus z2 is not analytic at 2 points, z equal to z1 and z equal to z2. In fact, it has simple poles at those points. But let's characterize this. So that's your complex plane, is z. Where is z equal to z1? And that's our contour is here. So it's a unit circle. Our unit circle, and I'm going to integrate in this direction. So that's my contour c 0 to 2 pi. Clear? Where is z equal to z1? 1 is -2 plus √3. I didn't get this correct, right? Plus minus everything. Oh, I was supposed to do it. Yeah, I think so. Okay. -2 plus √3 is √3 is about 1.7, right? So -2 subtracted out, there is remaining of -0.3 somewhere around that, right? So -0.3 is somewhere here, so it's surely less than 1. So that's the 1. That's inside the circle. What is important is whenever you're doing the integral, whatever is inside the circle contributes, outside the circle doesn't contribute. So here it is inside the circle. Z2 is -2 minus √3. It's already -2 is outside the circle. So you're adding 1.7 to that. So it's very much outside the circle. So it's Z2 is somewhere around. It's correct, right? Minus both are negative. Yeah, okay. So it's 1, so it's about 5. So it's somewhere here. So that's V2. So 5 times. Oh, sorry. 3 times 6, but closer. Yeah, 1.5. That's the important piece. You have to recognize which one is inside, which one is outside. That's the key piece in doing all these problems. That first of all, you have to find a contour on the complex plane, preferably closed. If it's not closed, at least part of it should be part of a contour that you can think of. And you have to recognize what are the poles of this. So this is Z1 and Z2 are poles, but only Z1 is inside. So from that point on, you say that I'm interested only in Z1, I'm going around it, so I is equal to 2 over 2 pi I. Right? And there is a residue, so there's only 1/4 of that, so that's 2 pi I. That's a residue. Right? Residue is 2 pi I times multiply, get rid of the Z minus Z1, so that's 1 over Z minus Z2. Evaluated at Z equal to Z1. Notice what I did. Remember your Cauchy's theorem is dz f of z over z minus a. If this is your whole, whatever is the remaining part should be analytic at that point, not everywhere, at that point. At z equal to z1, this function is analytic, right? It's away from that whole. So 1 over z minus z2 is not analytic at this point, but it is analytic at this point here. So this is analytic at z equal to z1. So I'd evaluate the function at that point because that's f of z, and that's my residue. And that's equal to 2 times z minus z2. So it is z1. I just try to substitute z1 minus z2. That's my result in a sense. So let's make this better. So z1 minus z2, how much is that? Minus 2 cancels out. Root 3 adds up, I suppose, right? Z1 minus z2, so it is 1 over root 3. Okay. Any questions on this? How we worked on? Again, usually it is like these are worked out problems. Once you teach it, it's kind of easy. But the main idea is to figure out what is a contour that you can pick, which serves the purpose of the problem. All the time, that's not obvious, especially if you're in a new model that you're building. You have to be creative as to how can you use your poles and the contour to get this. That is in physics. There is a very good application of this. You might have heard of Kramer's chronic relation. It's the optical properties of a material. Typically has reflection and absorption in it. Okay? So if you're passing light through glass, some of it reflects and some of it gets absorbed and some of it gets transmitted. These are the three things that happen. The transmission and the reflection is controlled by what is called the reflection coefficient. Okay? And the absorption is decided by the reflection coefficient, is decided by the dielectric constant, but it's decided by the real part of the dielectric function and the complex part of the dielectric function. And the interesting part is that they are different pieces of a contour. If you know one part of the contour, the other part is automatically decided. So the absorption inside an optical material is decided by how much it's going to reflect. So the reflection coefficient, the real part of the dielectric constant and the imaginary part are connected to each other. They're not equal, but they're connected to each other. And that's primarily coming because they're one part of the, so you draw a contour in the complex plane and one is related to the other. You would say, why do we have a complex quantity when you're talking about the optics of a material? Why? How can things be complex, right? Everything that we measure is real, right? So isn't that not everything is real? Remember that we work in Fourier transform most of the time. Like instead of the moment you say light, we like to talk in terms of color. Color is frequency. Frequency is Fourier transform. Fourier transform has this exponential in it. So complex refractive index is completely okay. Okay, so complex is part of it. The moment you go to Fourier transform, the moment you're doing optics in using colors, red, blue, green, that means you're working with complex quantities. So complex quantities cannot be avoided when you're working with colors or frequency in optics. Okay, so that's contour integral. Let's quickly say what's a branch cut, then do an example on analytic integration. And and there's a chance that I may not be able to finish this, but that's also part of your homework. I gave the homework, the last question in your homework is exactly what I will do here, but I want to do that slowly so that I can tell you a lot of relevant things. Okay. We said any function that is having an infinity is not analytic. Another way it is not analytic is if you have a discontinuity. Okay, so this is a complex plane, and let us say my complex, and let's say my function f of z is, let's say, square root of z. One would expect that that should be a very simple, innocent function. And this is a complex thing, remember? So this is immediately, think in terms of polar, it often helps. And this is equal to square root of r times e raised to I theta, then take a square root. Square root is, this is a positive number, so square root, we'll imagine this to be a square r raised to half. R raised to half and e raised to I theta over 2. Okay. And now if you notice, let's say that's my z. This is my z. And that's my f of z. Right. So remember, this is also complex, right? So I can put in a complex number, I get back a complex number. Let's say that angle theta is between 0 and 2 pi. So I fix my region there, and this choice plays an important role in branch cut. So let's begin. Let's say so let's start with a complex number z equal to I, right? So that's a possibility. I choose z equal to I. So that's somewhere here. That's fine, z equal to I. And my question is, what is the function f of z? Square root of z. So r is equal to 1 here. So that's equal to 1 times e raised to I pi by 2. Right. So what is f of z? So f of z is equal to, take a square root, since it is 1, square root of 1 is 1 itself. So this is, I have to take square root of that. So it is e raised to I pi by 4. So I have this 1 here, so that represents r equal to 1. And the same thing here, so that's your r equal to 1. And if I start from here, let's say this is the first number, the f of z will be pi by 4, so that's somewhere here. The point 1 in the complex plane got mapped onto, when I take the function, that became pi by 4, right? So that's down here. Is that clear what is happening? If I were to say z is equal to, let's, instead of I, let's talk in terms of theta. If I have it on r equal to 1, and if I do, let us say pi, that's equal to -1, right? So that's down here. So that's my second point I'm picking. Where does that go? F of z now is equal to e raised to I pi by q, right? Half the angle basically. So 2 becomes here, that's 2 is down here. Let's take 3. Oh, maybe we'll call this z1, z2. That's z1, z2. Just picking random numbers. So this is 1 times e raised to I 3 pi by 2. And 3 pi by 2 is minus I. Right? E raised to I 3 pi by 4. So the third point here corresponds to this point here. If I do z4, which makes a full circle by now, z4, that's 1 e raised to I 2 pi, that's equal to +1. F of z4 is equal to e raised to I pi, it's -1, so that's 4. I can, well, that's 4 is here. I can keep doing this. Did you see the pattern, right? It gets halved every time. The angle is getting halved. I can do this, keep doing this. 4. Notice the same point now. So this is 5. It is the same point, but now I have made 2 circles in here, and this will be 5. This will be 6. That's 7. And this is 8. And then it will start over again. So what is happening is that if I go 2 times here, I'm going once in this in the map plane. I'm doing this twice simply because it is z raised to half. It is very easy to imagine that if this was z cube, like cube root of z, then I can go 3 times here, and this will repeat after 3 times. 4th root of z, I'll go 4 times here and start repeating. If this was an irrational number, z raised to an irrational number, you'll never repeat it. Right? Irrational number will never repeat it. So you can have a lot of patterns in there. But now what you want to do is that, okay, you can go, your region is only from z to 0 to 2 pi. You don't go beyond that. You have to fix your domain. So we fix our domain to f of z. So get rid of all the 5, 6, 7, 8. That was just for demonstration. But my domain is only 1 to 4. That's going beyond the domain. 0 to 2 pi, if I restrict myself to 0 to 2 pi, then this is my domain. And now let me say, I want to approach a function from here. I approach it from here and here. Okay. That means to say in this complex plane, it seems like there are 2 close points. But on the map plane, they are very different points. One, like 0, like I said, this is 0 and 4. This is 0 and that's 4. They're very far apart points on this because of this property. So that means to say that f of z as limit theta approaches 0 is equal to 1. On the other hand, limit theta approaches 2 pi, theta approaches 2 pi, f of z is equal to, what is that equal to? -1, right? So this is 4.4 here, that's -1, right? So that's equal to -1. Whenever they are not the same, there is a discontinuity in the function. If they are the same, and I'm not only pointing 2 points, I have only talked about the angle, I should be able to come from any point here. Remember isotropic derivative. Analytic function means that I should be able to come from any point and it should be the same. That's a definite, or that's the idea of an analytic function. It is isotropic. It should not care for which direction I come from. I just chose to come from an angular distribution. So this is not analytic. So this is f of z equal to square root of z is not analytic. I don't have to worry about just r equal to 1. I could have chosen any r, right, and have the same problem. So it's not analytic along a line, which is theta equal to 0. So if I were to draw this is z, theta equal to 0 is a half line. Every point there, if I come from the top, I'll reach a different point. Top and the bottom, so this point will be very different from this point. So this is non-analytic. So whenever a function is not analytic along a line, complete line, and it is of this kind, usually related to a power, you can extend it to a power, can always be controlled in terms of a logarithm, then you say it is a branch. Notice why this theta equal to 0 was nothing special. This theta equal to 0 came because I decided to choose my angle to be 0 to 2 pi. If I had chosen, if we choose theta to be -5 to +5, actually let's say less than or equal to pi, that's a perfectly valid choice. If I were to give you half of you to do an analysis, many will pick 0 to 2 pi, many will say, oh, I like -5 to pi. Perfectly fine, that should not be a problem. Then, but they will conclude the analyticity differently. They would say it is not analytic along this line. Right, so it depends on the choice of your domain. So a branch cut is not unique in that sense. If you have a branch cut, usually there is a branch line. So this is called maybe this is a branch point. There is a branch point. This is a branch line or a branch cut or branch cut. Branch point is important and it could be any curve. So branch cut or branch line, cut or line could be any curve connecting the branch point and going to infinity. So the only requirement is that you start from here and go to infinity. For example, this is also a valid branch. I can go along this line. Like I can come up with a very fancy choice of angle theta domain where I only have to cut the complex plane into 2, right? Theta goes from this way. So it will be a very complex choice of your coordinates, but in principle, that's perfectly fine. And along that matching point, that's where the cut will. What you want to take home is that whenever there is a z raised to a fraction, so if you have z raised to a, If A is not an integer, it will lead to branch cuts. Okay, very simple function like z, square root of z, cube root of z, always they will be having branch cuts. And then they're not always bad, as I will show you in the example we are going to do now. We can exploit this. Often they are very useful. Any questions on what a branch cut is? Okay, so now we're doing analytic continuation. An example. Whenever you have a function, you want to extend its domain. For example, sine of z, sine of x, right? Usually, x is real, right? Think of binomial expansion, right? First you do it for integers, then you say that, oh, it works for any number. Similarly, sine of x, x is real, but why should x be real? V can be complex, right? Like z is complex. And the same expression works. Sine of z is analytic. So in real, sine of x, this is x minus x cubed over 3 factorial and so on. So it is z minus z cubed over 3 factorial and so on. So you didn't have to do much. You just said that z is, from tomorrow onwards, z is complex, and everything that you knew about sine function went through. That's a luxury. Not all the time that is possible. An example could be n factorial. N factorial is equal to 1 times 2 times 3 times so on until n, right? That's a definition of a function. This works when n is equal to 1, 2, and so on, right? What is 1.5 factorial? 1.5 factorial? Or 0.5 factorial? Right? Apparently, you cannot do this here, right? But you generalize. So this is what is called analytic continuation. That you say that, oh, okay, so that is a function which is n plus 1. This is equal to 0 to infinity dt over t raised to n and e raised to minus t. And this is allowed for n real. So as far as real part of n is greater than 0, you're good. So 0.5 factorial here is allowed. If you say that this is the extension of this, so you say that this is called the gamma function, by the way. Gamma function is an analytic continuation of n factorial, in the sense that n factorial is only true for integers or positive integers, and here suddenly you can extend this further. And you will really say that, oh, what if I want to go even further? Then you would like to do it for an old complex plane, and that's the questions you ask. So let's do a simple example. Gamma functions are all a little elementary, but still they're all built on the same idea. So let's do the example of simpler example of 1 over s. A simple function, and a way you can evaluate this is that you do so this is the given function. But observe So observation is that there is an integral associated with that. So for example, if you were to do 0 to 1, think 0 to 1, and dt over t raised to t raised to s. Can you do that integral? That should be straightforward.
Plus one is one.
So, yeah. So this will be
T2 plus minus one.
1, and then you raise it, right? So it is t raised to s over s. Evaluate it at s equal to 0 and s equal to 1. Right. No, not s equal to 0, right? T. Sorry. T equal to 0 and t equal to 1. That's equal to t equal to 1, that is 1 over s, and t equal to 0, that's 0. So apparently this integral is a good representation of this. Okay? So the point is this really true? Like, is it always true or not? Let's check that out. Remember, you have the square root of z that we did example just now, right? It's as a branch cut and so on. So how can we use those features? So let us try to extend this everywhere. If you were to want this function, let us say f of z, right? F of s here, which is basically 1 over s, but you are thinking in terms of this integral and you want to really work in the complex plane. It's a little misleading because this is a simple function. You know the exact solution. Generally, you don't have this luxury that you can think of it as 1 over s. Think that you have a function which is really in the form of an integral. And gamma function is a classic example. Like whatever we are doing here can be used to analytically continue gamma function. So you would like to do this analytic continuation. So you will say, so let's consider the following function. Since there is t raised to s, the same problem comes that there is a branch cut, and this is your branch cut associated with this function. And let's say you go from, this is 1, that's z equal to 1, that point is equal to 1, and you go this way. It's not a closed contour, so you cannot use Cauchy's theorem immediately, and it looks like this, right? So this is your z point. I have to now define my function itself. Let me choose that function to be. Let me refer. What do I call it? Yeah, so it's the same thing. Just I have to, and I call it mu of. Yeah, let me call this mu of s. This is in your homework. I define a function mu of z, which is equal to 1 over 2 pi e raised to, and this s. E raised to I 2 pi s. And why e raised to I 2 pi s? Remember, square root of z had a branch point, and I'm trying to capture that. and you go through the contour, which is this contour, C. And you do dz over z times z raised to s. Same idea as this, but now this was on a real line, right? It was going 0 to 1, but now I'm going on a complex plane. I'm not really touching the point. Like I'm staying away from all the non-analytic points. And this, the idea is that this is valid for all s. You're extending it to all regions of the complex plane. But how do you go about this? So this is a good demonstration of how this discontinuities come in. Let us go along. You go counterclockwise, right? So let's say, but in this case, it should not matter, I suppose, because it's not a closed contour. But still, let's say this is C1, that's C2, and that's C3. So I go in a circle, C1, and notice this doesn't really go all the way go to the y-axis. So we have to be careful about that. So let's begin with contour C1. On the contour C1, we are pretty much hugging the real line, the positive real line. So z is equal to r e raised to I. Theta is really tiny, so it is theta where theta approaches 0. That's what we are doing. So we just pretty much the same as when theta goes to 0. That's e raised to I 0. That is 1. So this is pretty much r. And my integral will be, so along C1, so this is e raised to I 2 pi s minus 1 d1 dz over the z raised to s minus 1. Or maybe dz over z times c raised to s. That's the same as e raised to I 2 pi s minus 1. dz is the same as dr. So I'm going from z equal to 1 to approaching 0. So this is r going from 1 to, it doesn't go to 0. So that is a small limit, right? Let me call that epsilon. Like I really don't touch it, right? That is, I'm limited by the circle. So r equal to epsilon and what? And dz over, so this is dr over r and r raised to s. Simple relation here. So, but this can be done. This is r raised to s minus 1. So this is equal to r raised to s minus 1. So that's r raised to s minus 1 s divided by s 1 over e raised to I 2 pi s minus 1. It's still readable. That's equal to r equal to 1, r equal to epsilon. Can you move the camera a little so that I can go a little further so that I know where to do the next down here. So this is epsilon raised to s. Epsilon raised to s and then 1 raised to s. 1 raised to anything is 1, so it's epsilon raised to s minus 1. Think so. Yeah. All right, that's for C1. If I do this for C2, let's do this. Yeah, first C2. C2 is a circle, so it is circle of radius epsilon e raised to I theta, where theta goes from 0 to 2 pi. And dz will be equal to epsilon is fixed now. So I epsilon e raised to I theta. Theta. So my integral becomes CQ over C. Let me do this right here itself. The dz is I epsilon e raised to I theta theta. Z is again I epsilon e raised to I theta. And z raised to s, which is epsilon times epsilon raised to s times e raised to I theta s. Epsilon e raised to I theta cancels out, and I'm going from 0 to 2 pi now, right? But this is 0 to 2 pi. That's equal to epsilon s I times epsilon s over e raised to 2 pi s minus 1. So this is e raised to I theta s, so e raised to I divided by I times theta, evaluated from theta equal to 0 and theta equal to 2 pi. Usually when you go from 0 to 2 pi, it comes out the same values, except when it is square roots, or it's not an integral root. The I cancels out, and we get no IS, right? IS. So I have 1 over, so this now becomes e raised to I 2 pi s minus 1 divided by s times what's equal to 1 over s. Okay, so that's a nice part in there. But we have to be careful still, because you don't know what happens at this point, right? Those cancellations have to be happening. This still seems to be contributing, but hopefully this cancels out. So let's say C3. C is equal to, again, this time C3 is here, so R e raised to I theta, where theta is approaching 2 pi. So that is innocent. So you would say it is simply e raised to I 2 pi. But be careful, this you shouldn't make this 1 again. Like at this point, you shouldn't, because z has to be evaluated, right? If it approaches s, if it comes in touch with s raised to s, then it contributes. So again, do the same thing. So we have 1 over exponential I 2 pi s minus 1. This time on the contour C3, where now we are going along R. So R is going from epsilon. R goes from epsilon to R equal to 1 on the bottom R line. Right? So it is R. So from here to there, and again do dz over s. So I will do z is so much, so dz is equal to dr times e raised to I 2 pi. So it is dr e raised to I 2 pi, well v is also r e raised to I 2 pi. So e raised to I 2 pi cancel out, and r raised to s, that is r raised to s times e raised to I 2 pi S. Pull this all out. We still again get the same thing, except we are going from epsilon equal to 1. That's equal to e raised to pi s over e raised to pi s minus 1, and the integral is epsilon to 1 d r over r and r raised to s. R raised to s minus 1, that's it. At this point, it's good to say r raised to s. That's r raised to s. S divided by s. So this would be e raised to pi s over e raised to pi s minus 1. And r raised to s over s, so this is 1 over s. R raised to s, that's 1 minus r of epsilon, so epsilon raised to s. So overall, we are add all these things. That's what our answer will be if I were to ask you to evaluate this mu of s on this contour. So I have to add all these quantities out. And let me do this here. Mu of s equal to, let me make sure the things. Yes, so. So this is all. We have, let me take the common things out. And s is also common now. Yes. So you have epsilon s minus 1. Second one, we just have, instead of writing this one, let's go here. E raised to pi s minus 1. And then we have this piece. Think that these things cancel out, but it's not really this canceling this. One would naively think that, oh, these two are canceling out. It's not. The cancellations are happening right at this point, wherever the divergences meet. Each term, in a sense, is divergent. So it's like by s times 1 epsilon raised to s. So let's see, how does this work? Let us cancel. Okay. No, because we have e raised to, yeah, that's what things, because this is also. Okay, so what is this equal to? What is, at least that is -2, let me at least know it comes, so it's -2. And then there is 2 of this. So it is plus 2 times e raised to I by s. And what is remaining is epsilon s raised to s times okay. Am I not seeing the pattern? epsilon s minus of epsilon s times e raised to I 2 pi s. It's all. Limit epsilon tends to 0. 1 over 1 I 2 pi s minus 1 over s times yes, second. I think I'm missing something. So let's see here. Oh yeah, so something is missing here. Yeah. So I'd say there's an error here. So what did we miss? Yeah, here, right? There was this epsilon raised to s, right? This went here. And from here to here, I forgot to carry it along. I took care of this s here. I canceled, but this I forgot. Because that's an extra piece there. So I forgot this piece, I think. My bad. Oh. This piece I didn't carry it along. So this should have been, if you allow me, epsilon s. So the squared quantities I'm introducing at this point. You check your notes, and this is missing. Right, and this is then epsilon raised to s. You agree? So that changes everything. So I have to go back. Sorry about that. The whole thing is about the cancellation and I missed. So that's that small piece. Okay. Now let me try again. So yeah, let's just open this. -1 plus epsilon s raised to I 2 pi s minus epsilon s plus raised to I s and then minus epsilon s minus So usually the point here is that these two cancel out. These two cancel out, these two cancel out. Whatever is remaining is exactly the denominator. That's, let me write this in 2 steps. One over. And the whole point here, the emphasis in impact here is that remember, as you get closer, right? Whenever you get closer to this point, that is that could be an infinity if this was in the denominator, right? If this was in the denominator, that could be an infinity t raised to, for example, if s was like if this was in the denominator, then this could be a non-analytic function. And that whole feature can be captured just by going around it. So epsilon tends to 0. In this case, it may not be harmful, but whenever you're doing a gamma function, that it can be or the features of epsilon of the zero doesn't hurt the integral. That's the point we want. Yeah, sorry about that error. So hopefully that didn't distract you too much. I'll stop here. Try to think about what's going on. This is much more deeper, or maybe a quiz, right? So what is 1 plus 2 plus 3 so on equal to? You might have heard of this at a popular level.
N minus one.
It goes all the way to infinity. So it's divergent, right? I mean, it should be divergent. But if you have read popular stuff these days, you have YouTube, search for this 1 plus 2 plus 3. This comes out to be equal to minus 1 over 12. Add all positive numbers, and you get a negative number, and it's less than 1 in fact. Okay, so it's very weird result, but this is not really the sum of these quantities. It is like saying 1.5 factorial. What do I mean by 1.5 factorial? But this can be continued into a function whose value is minus 1 over 12. So the quiz is, what function is it? Okay, so show that this is actually equal to minus 1 over 12 in some form. Don't like to prove it, that's difficult, but hint is Riemann zeta. So what is Riemann zeta function and zeta of minus 1? Okay, so that's the symbol for Riemann zeta function. Evaluate Riemann zeta function, use quiz, right? Use Mathematica. You guys said you're not used Mathematica. This is a good time to start using Mathematica. In this computer lab, you have Mathematica. Just type Mathematica, it shows up, or click on Mathematica, it shows up. Not actually Google these days can evaluate Riemann zeta function minus 1. So try to use Mathematica just to, if you have never used Mathematica, try to open Mathematica and it's just to make you practice to start using Mathematica. Mathematica is a paid software, so it's not a good idea for me to recommend using that, but it's very useful. That's I can say. Thank you. I'll stop here. Yeah. Oh, I went 2 off. Sorry. It's 10:59. Okay. My bad. See you, Niranjan. Yeah.
Thank you, Dr. Sajas.
Bye. Yeah. I'm sorry, I didn't realize the time was that. I'll do this. You have to. Oh no, you don't
No,
have a class. But I
not
can
today.
manage. Oh, thank you.